let's get this going. All right, so the last topic I have from this chapter on numerical integration, because we are going to circle back around to integration later, is Romberg integration. Okay. Now, it's actually very easy to describe Romberg integration in terms of existing concepts, because they're basically taking two existing items and merging them together. So Romberg integration is simply a composite trapezoidal rule combined with what I covered last time, Richardson extrapolation. So what that means is you compute initial approximations using the composite trapezoidal rule, like for certain h, and then h over 2, h over 4, and so forth. And as you do that, you use those approximations to extrapolate, using Richardson extrapolation, that formula, to get more higher order accurate approximations, and you keep going as many times as you can to improve the accuracy. And that's really all that you need to do, because it uses the fact that the error in the composite trapezoidal rule has this form, so the exact integral minus the composite trapezoidal rule approximation, which is h over 2 f of a plus a sum 2 f of xi plus f of b is equal to some constant h squared plus another constant h to the 4, even powers of h. And the reason how we know that is what I also did last time, that Euler-Maclaurin expansion. The most horrendous exercise in integration by parts that any of us have likely ever seen. Okay. So because of what that expansion gave us, we know it has this form, so we can take advantage of that to perform Richardson extrapolation. Okay. So what I'll do is, well, actually, I'm going to change the notation a little bit to conform to the notes. I use k's to indicate these constants, just so you can, in case you're following along with the notes. Okay. So the way I'm going to do this is generate what is called a Romberg Table that includes approximations of varying orders. So what I'll do is I'll start by showing how to generate the first few entries of this Romberg Table, and then I'll give the general algorithm to perform as many extrapolations as you want.
Why did you change those in case?
Oh, just because I use k in the notes.
Okay.
Yeah. Okay. I try to stay consistent, but okay. So we use spacing h, well, labeled as h sub k, is b minus a, so the width of your interval, times 2 to the minus k. So your initial spacing would just be b minus a, then b minus a over 2 over 4, and so forth. So what we do is we compute the following. My first approximation I'll call T11, and that's just the basic trapezoidal rule. So this is with spacing h naught, which is this b minus a. Okay. Then I compute another approximation, and I cut the spacing in half. And I'll call this new approximation T21. So it's b minus a over 4, which is the same as h1 over 2. So my spacing now for this one is h1 b minus a over 2. And just like how this is h naught over 2. And I have f of a plus 2f of the midpoint, a plus b over 2, plus f of b. So here I'm just using 2 trapezoids. Okay. Now, the composite trapezoidal rule has order of accuracy h squared. That's the leading error term at k1 h squared. So the error has this form. So its first approximation is equal to the exact value, which I'll call I of f. This is exact integral. And then the error is k1 h squared plus terms of order h to the 4th, where in this case h is just h naught. Okay, b minus a. And then the next error term is equal to the exact value plus an error term k1 h over 2 squared. Okay. Plus, again, order h to the 4th. And we worked this out before, actually, based on what I have over there. Should have minus. Not that it really matters, but okay. The point is, it's a constant times h over whatever squared. So we worked this out before as to how to do the extrapolation. So by extrapolation, we can do approximation I'll call T22. And that equals T21 plus T21 minus T11 all over 3. Because you divide by 3 if you have second order accurate approximations. That's what we saw last time. And this is equal to the exact plus some new constant, which I'll call K2 tilde h to the 4th, plus other terms that are order h to the 6th. So my first approximations with the second index being 1, these indices indicate rows and columns in your Romberg table. So the first column is just composite trapezoidal rule. The second column indicates one level of extrapolation to go from second order accurate to fourth order accurate. So right now I have 3 entries in my Romberg table. So I have T11, T21. These are extrapolated to give me T22. Okay. This is second order accurate. This is fourth order accurate. So this is what I call my Romberg table. All right, so it starts out with this. Now, suppose I compute another trapezoidal rule approximation. I'll call it T free one. So this would be using spacing that is b minus a over 4. Then I can extrapolate between these two to compute a second approximation over here, which I'll call T free 2. So that is also fourth order accurate. So now what can I do with these guys? Extrapolate again, which I did last time in the derivative example. Get a new value, 333, which has one order of accuracy.
8
No,
or 6.
6. Yeah, it increases by 2 additively.
I knew that, but for some reason my brain said double.
Okay.
But,
Yeah. And so in this case, T33, first T32, use the same formula as for this one, just different approximations. And so it's T31 plus T31 minus T21 all over 3 to get this one. And then to get the next approximation, a 6th order accurate, so it's T32 plus T32 minus T22. But if it's fourth order accurate to start with, I'm not going to divide by 3. What am I going to divide by instead? We saw this last time.
Wait, repeat that?
Okay. When I took these second order accurate approximations and extrapolated to get fourth order, I divide by 3. When I extrapolate from these fourth order approximations to get the sixth order accurate one, I'm not going to divide by 3. I did this last time. I divided by what? You can look at your notes if you want.
6.
No.
Got it. 2 to the power of 4.
What?
Yeah, that's right. Is it minus 2 to the power of 4 minus 1?
Minus 1. Yeah, you were so close. Yeah, 15. Okay. Yeah, so it's always 2 to the p minus 1, where p is the old order of accuracy. So, because you're trying to extrapolate, like in here, you're extrapolating from second order to fourth order. So for these extrapolations, p would be 2. So you have 2 squared minus 1. Here is order 4 to order 6, so it would be 2 to the 4th minus 1.
Whenever we're doing the order, we do the degree of the whatever the k term is with, right?
I'm sorry.
Since that's
Yeah, that's what you're trying
x
to.
to the 4th, that's
Yeah, because that's what you're trying to cancel.
Okay.
Yeah. Yeah, because what happens is, after getting this extrapolation, you get this, and then when you do this one, you're going to have similar thing, k2 tilde h over 2 to the 4th, and that's what leads to that. Yeah. So, actually, I think last time when I was introducing extrapolation, we worked out a general formula where you're cutting by a factor of q and it's order p accurate and all that, and so it's all there. But okay, now okay. So what we could do is, if I were to compute more approximations using composite trapezoidal rule, I could take this out even further. If I compute one more down here, then I can extrapolate to this column, and then I can use 2 approximations here to get something 8th order accurate. So I would divide by, instead of 15, it would be what?
So that again, I'm sorry.
If I were to do this one more time, like go all the way out here.
Oh, you would do 2 to the 6.
Minus
Yeah, so 63. So, Okay, so, so now we see the pattern of how we generate higher order accurate approximations. So now what I'll do is describe the general algorithm. Last one.
Thank you all.
It's a season to get sick.
Oh,
Yeah. Well, I learned something new. It was last week, actually. I guess when someone has a cold, I guess a stubbornism, they call it the crud. Yeah, I hadn't heard that before in that way. Yeah.
I got the credit. It's just right. I don't know. Just means you're sick.
Okay. Now, okay, so the algorithm for Romberg integration. Okay. So what you do is first you set your spacing just to be b minus a, because you're using the simplest possible instance of the trapezoidal rule. And you have a loop. All right, so you're going to fill out a Romberg table. You can think of it as being like the lower half of a matrix, like a lower triangular matrix. That's going to be capital J by capital J. And what you do is, first you compute an approximation using a composite trapezoidal rule, using, oh god, do I have a typo in here? No, I don't. Well, hopefully I don't. I've fixed some typos in here before. We'll see how it goes. All right. So I have h over 2. So this is just composite trapezoidal rule. Now, what I'm doing here, okay, so this is composite trapezoidal rule with 2 to the j minus 1 subintervals. Okay, because when j is equal to 1, I'm only going to have one trapezoid, so I need 2 to the 0, and then it's going to keep doubling after that. So, the number of interior points is going to be 2 to the j minus 1 minus 1. So watch your font sizes, or what's subscripts or superscripts. Okay. And when you evaluate at the interior points, a plus I times h, so this is like xi. Okay. And then you have f of b. All right, so that's your composite trapezoidal rule. Now, once you have that, then you perform any extrapolations that are possible. So we need an inner loop for that. For example, if I compute a t for 1 down here, I can do an extrapolation here, here, and here. So, so we can fill out extrapolations in columns 2, 3, etc., all the way to, not capital J, little j. So for instance, the first time through when I only have one trapezoidal rule approximation, I can't do any extrapolations yet. The loop would run from 2 to 1, so it won't run at all. The next time around, when little j is equal to 2, I have a second composite trapezoidal rule approximation, and I can do one extrapolation. This loop will run one time. And each time you use the composite trapezoidal rule again, you can do more extrapolations. So here you use the Richardson extrapolation formula for whatever order of accuracy you want. So T row little j column, whoops, I forgot my loop variable, for k equals all these guys. Okay, so this extrapolation in column k, each time you do an extrapolation, you are reaching back to the previous column to take two approximations and extrapolate from them. So it'd be t, j, k minus 1 plus t j k minus 1 minus the approximation right above it. So it's row j minus 1, same column as this one. And then you find the right thing to divide by. Now if you notice, what did we divide by before? 3, then 15, then 63, and so forth. All of those are powers of 2 minus 1, but what are they also powers of minus 1? 3, 15, 63, powers of 4. Because, so we can work with powers of 4, not powers of 2, because it's only even powers of 2 minus 1. But what is the even power of 2? It's power of 4. So I can say 4 to the k minus 1 minus 1. So that gives you the right value to divide by each time. So for instance, when k equals 2, you're going from second order accurate to fourth order accurate. So 4 to the first minus 1, and you divide by 3. And then next time around, 4 to the 3 minus 1. And so you get 16 minus 1. So it works out as the same way as what I had in the previous board. Okay, that takes care of your extrapolations. And then you cut h in half for the next time. And that's the algorithm. So when you finish this algorithm, the last extrapolation, T capital J, has order of accuracy h to the 2 capital J accurate. So for instance, if you just do a 2 by 2 Romberg table, so capital J is equal to 2, you're going to compute two trapezoidal rules and then a single extrapolation that's only going to give you fourth order accuracy and so on. Okay, so you can do this as many times as you want to get whatever order of accuracy you want.
So J is something that is given.
Capital J is.
Capital J, right?
Yes, you choose that.
Okay.
Okay. And I have some code on the site. Quad Romberg .m. That's on the lectures page. That carries this out. So you can try it out. All right. Now, I want to do an example of this. But before I do that, I want to point out that the way I've written this algorithm is actually, there's an inefficiency about it. And the extrapolation part, there's hardly anything going on here. There's just a few floating point operations and that's it. Here is where the real work is being done, to use the composite trapezoidal rule. And we want to minimize the number of function evaluations of f. But the way I've written it, this line is wasteful. And the reason why is, every time you use a composite trapezoidal rule, so if I use h equals b minus a, which points am I evaluating at? A and b. Then I cut spacing in half, b minus a over 2. So now I have two trapezoids. What points do I use? A, the midpoint, and b. Then I cut it in half again, b minus a over 4. So now I have 4 trapezoids. So I use A, this point right here, which is a fourth away there, and this point again, this point again. So look what happens is you cut h in half, every single point that you plugged into f, each function evaluation is being used again the next time down. These are the new points that are filled halfway in between. So basically, half the work, roughly half the evaluations that you need to do have already been done. So to simply implement this formula as written would duplicate half that work. So you want to avoid that. So how can you best take advantage of what you did before to avoid having repeated function evaluations? So what we can do is look at this formula more closely and see how to do that. So if I express one of these trapezoidal rule formulas, but what I do is I take the summation in the middle, and I break it down into odd numbered and even numbered points. So first I have odd numbered. So that's going to be 2 to the j minus 2 points. And this, so for my odd values of I, and then I do it again. Let's see. And notice, if you look at the previous board, I always have an odd number of interior points. So, so I have 2 to the j minus 2 minus 1. So I have an even number of points here and an odd number of points here. And this would be f of a plus 2ih, and then plus fb. Okay. So this is equivalent to what's over there. I've just separated the odd numbered and even numbered interior points. Okay. Now what I'm going to do is I'm going to rearrange this of f of a, and then I'm going to have the sum involving the interior points. So that would be 2I equals 1 to 2 to the j minus 2 minus 1. And we're going to write it as f of a plus I times 2h plus f of b. And then I have this, this other sum. So I have h over 2, and then I have 2 times the sum over all the odd number points. Okay.
Why don't you use j minus 2?
Oh, because if you look over here, we have 2 to the j minus 1. This is how many interior points we have. But now, if we're cutting those into two groups, how many is in them should be roughly half of this. So that's why the exponent decreases by 1. Yeah. So, like in the case where I have h is equal to b minus a over, let's say, 16. Oh, there's going to be such unequal spacing. Okay. So I have x1 up to x15. I have 15 interior points. But then if I look at the odd numbered ones, okay, so 15 interior points. How many odd number ones do I have? 1, 2, 3, 4, 5, 6, 7. Okay, and then I have, no, 8. I forgot to count this last one. Okay, and then I have 7, so this is odd numbered, and 7 even numbered. So the number of even numbered interior points is always a power of 2 minus 1. So here we have 2 to the 4th minus 1, and this is 2 cubed, and this is 2 cubed minus 1. Right. Now, the reason why I wrote this way is I times 2h. This looks like the trapezoidal rule again. If it's the same form, it's just with half as many points, with twice the spacing, 2h. So the difference is if I was really doing a trapezoidal rule, I would have let's see, 2h over 2. So I should have an h here, but I don't. I have h over 2. So this first part is actually equal to the trapezoidal rule at level j minus 1, but multiplied by a half. So that covers this piece. And then I have this other sum to deal with, so that would be, well, the h over 2 and a 2 simplified to h. So this, here are the new function evaluations here. So really what I should do is modify the algorithm written on the previous board to say tj1 is actually equal to this. That maximizes efficiency. So the only function evaluations being done at each iteration are new ones. So that is actually going to cut the work by, let's see. Actually, it's going to cut the overall work in half. So that helps. Okay, so any questions about what was done here? There's a lot of symbolism involved, but okay.
So we're just using the shorter version for.
Yeah, we're reusing information we have, and it's just because of the fact that when we double the number of trapezoids, every point at which we evaluated f before, we would evaluate again. This recognition of a savings is also how the fast Fourier transform got developed. Because the way a fast Fourier transform works is you're trying to compute a Fourier transform of evaluating a function at equally spaced points, and then you separate them into odd and even numbered, and you realize, well, the even ones, you would also use those in a transform of half the size. Just with double the spacing. And so, again, similar savings can be realized to generate a more efficient algorithm. So there's a lot to be gained by looking at, when you alternate things between odd and even numbered. In fact, well, those of you who were in the KSS meeting last hour saw me exploit the same thing. Okay. So now if we, to give you an idea of how well this works, I'll show you the errors that you get from an example. I did this before with derivatives, but now with integrals. So the integral we're evaluating is integral of e to the minus x squared from 0 to 1. Now this is one that you cannot compute an antiderivative of this. There's no antiderivative of e to the minus x squared using elementary functions. So my Romberg table, so I'm just going to list the errors. That's really the interesting part. And I'm going to carry this out to just 3 by 3, so up to 6th order accuracy. So I perform basic trapezoidal rule. So for here I have T11. Actually, I'll use a little more space here. So this is 1/2 f of 0 plus f of 1. basic trapezoidal rule. So this gives me an error of nothing great. Okay, 0.63. So, I have only one decimal place correct. Then the next trapezoidal rule, where I use two trapezoids, that should cut the error roughly by a factor of 4, because this is second order accurate. And sure enough, it does roughly 0.015. But again, not great. And then I do it again, and now be okay, so the error in that case would be 0.0038. So again, roughly a quarter of this. So the behavior is like you'd expect. So then I extrapolate between these two. T22 is T21 plus T21. And we divide by 3, because these are second order accurate approximations. And the error in this case, after a single extrapolation, is 0.00036. So for such little work, this was gained us a lot of accuracy. But one thing I want to point out about this very first extrapolation, if I fill in what these are, so I have, so this is equal to, well, another way I could write this using, by putting these two fractions together and using a common denominator, this is equal to 4 T21 minus 3 T11 all over 3. I wrote it that way before, last time. So that would be, if I work that out, that would be f of 0, so 4 times this, f of 0 plus 2 f of a half plus f of 1 minus 3 times the first trapezoidal rule approximation. So that would be 3 halves f of 0 plus f of 1 all over 3. Although something seems fishy. Oh, no. No 3. Yeah. So minus 1/2. Okay. That makes more sense. Okay. Now, if I simplify this, so I'd have 1/6 f of 0. And then I have 2 minus a half. Actually, I only have this. So 4 f of 1/2. Because I have 2/3 f of 1/2, but that's 4 over 6. And then for f of 1, I have 1/2 divided by 3. So f of 1 over 6. So it simplifies to this after I put all this together. But can anyone tell me what that is? What rule that is that you've seen before?
Simpsons.
It's a basic Simpsons rule. All right, so, and the thing is, Simpsons rule, we saw it's fourth order accurate. So the first extrapolations of composite trapezoidal rule actually give you Simpsons rules. Okay, so then we extrapolate between these two to get T32, which is T31 plus T31 minus T21 all over 3. And the error in that approximation is 0.00031. Oh, I'm sorry, I goofed in this one. 0036. I had 38. No, hold on. I'm looking at the wrong place in my notes. Okay, sorry, it was right before. Okay. So the error from here to here goes down by a factor of about 16, because it's fourth order accurate. And finally, I go one more time to, so this is order h squared, order h to the 4th, and then order h to the 6th. So that would be T33, which is T32, so I'm extrapolating from these guys, plus T32 minus T22 all over 15, because you're working with fourth order approximations. And the error in this case is 0.000096, so notably more accurate than before. Okay. So there you have it. That's how Romberg integration works. So actually, if I were to write these in terms of a more efficient approach, this would really be 1/2 T11 plus, in this case, it would just be f of, okay, make sure I have this right. Let's see, I have 1/4 plus 2. Okay, so 1/2 f of 1/2. Okay. And then this next one would be 1/2 T21 plus 1/4, because this is the h for this level, and that would be f of 1/4 plus f of 3/4. So what we see here is what are the new values being added in to improve, to avoid wasteful computation. Okay, so any questions about how Romberg integration works? And if I wanted an 8-fold accurate approximation, I would have to fill in one more entry in this column, and then I can keep extrapolating to go one step further. Now, I can't resist the opportunity to give almost like what parents or grandparents do to their children, give a in my day story. So when I first took a first numerical analysis course of a counterpart to 460, which is at Purdue in 1988, now it's actually in the computer science department where it was taught, because computer science was more mathematical back in those days. On the final exam, I had to carry out Romberg integration.
Oh, sorry.
It felt like it. That was good. Yeah, on paper by hand. So I had to memorize this algorithm, and
Wow.
yeah. So yeah, I wouldn't dream of putting in. Well, interesting idea, but so okay, fine. So,
Yeah.
And then you have to just print out each part.
yeah. Okay. Sure. Yeah, and I wish I could remember what else they had us do. Well, okay, another one from the same class where we covered Gaussian elimination, linear systems, and all that, like LU factorization. So on the test, they gave us a 3x3 linear system to solve, and so I go through the steps of Gaussian elimination, and then forward substitution, back substitution, all this stuff you're going to hear about in 610 if you don't know what I'm talking about. And I felt I did it right. And then after I left, I talked to a classmate about that problem. And he said, well, he just got 101. I thought, oh, great. Because you know how it is. They make the numbers work out nicely, and that's how you know you got it. And that's warn my students, no, I don't do that all the time. So don't just assume that. And I thought, so this was on a Friday. So I had the whole weekend it's Thursday for a Tuesday, Thursday class. So I had 5 days to stew over like, oh God, I messed this up. What else did I mess up? How many points are we going to take off, et cetera, et cetera. And then it turned out that I made one tiny mistake toward the end, and they were very generous with partial credit, so I still got like a 96, way better than he did. So my class really hated me. So and the thing is, it was a computer science class. All computer science majors had to take it, and all math majors didn't, unless they were like in the applied math option. And I was just a sophomore and a math major with all these juniors and seniors who were in computer science, and they really hated me. So I guess I was one of those people who blew the curve on the tests. But that's when I discovered I loved numerical analysis. And so 28 years later, here I am. Yeah, well, because I was majoring in math, computer science. I wanted something to blend both of them, and I had no idea what that would be. And then I discovered this. It's like, oh, okay, problem solved. Okay, so, and that concludes this chapter on integration. How am I doing on time? Not so good. Yeah, so I feel myself continuing to fall behind, which I guess bodes well for you guys. I'll call on you sometime. Although I guess what I have for this next chapter, I don't have much in the way of notes, really. So I may, we'll see. Be ready. Do the next problems. Okay. Well, okay. How many of you have gotten to start on like the first take-home test problem, that batch? Anybody?
The fun stuff.
Like actually trying to work a problem out.
Okay, I started one.
Okay.
Those are that.
And you're not even officially in the class. So
Yes, but
okay. All right. Well, that's good though. So what's the rest of you guys? No? Okay. Yeah. What?
I mean, I asked you questions about some of
Okay.
them.
Okay. Yeah, because nobody has asked me about any of these.
I
Yeah.
did.
Which one?
In our meeting last week.
Um,
Those questions I asked you, those were.
Oh, I just assumed that those were like homework things. Okay.
They are homework problems.
Well, yeah. But, okay.
Yeah.
Well, okay. Sorry. Okay. Okay. Now, so to this next topic. Those of you who have taught, which I guess is most of you, maybe all of you on some level, or okay. Oh, okay. Well, that'll be fixed soon enough. It happens now and then. I mean, even if you're teaching a class of generally alike, you get to a topic, you see that that's the topic you're supposed to cover today, and you're like, fine, I'll cover it. And there have been times when I've gotten more experience, like tenure track level, where I'm like, no, I'm not covering it. And I'm really not supposed to do that. I wouldn't do it if it would affect a future class, like in a sequence or something, but there are times when I want to. So this is one of those times. So, and the reason why is, what we've seen all semester long is, here's a certain problem we're going to solve using some numerical method. I present the algorithm, and the algorithm actually works, and at least you're left with some sort of systematic way to approach the problem. And for this problem, I can't give you that. It doesn't exist. So this is really more of theoretical interest. So this is chapter 8.
Chapter 8
In the text. There's chapter 4 in the notes. It's not a very big chapter, the notes. Polynomial approximation in the infinity norm. Okay. So first, I need to acquaint you with the notion of vector spaces that are spaces of functions. So the vectors involved are actually functions. Okay. So first, the dilemma. Because we already know how to approximate functions by polynomials doing what? How can we, based on what we've seen so far, I want to approximate a function of a polynomial. What can I do?
Sorry, can you repeat the question?
If I want to approximate some f of x by a polynomial, what can I do? Polynomial interpolation. You can use Lagrange, or if you have the information, Hermite, whatever. You can do that. But the dilemma is, at least we've seen in some occasions, polynomial interpolation fails miserably. It is not necessarily a good tool for approximating f of x on a given interval AB. So yeah, if a polynomial hits f exactly at certain points, your interpolation points, but you don't know what's going to happen in between. And that's not good enough. Now, there are certain remedies that can help, like using Chebyshev points instead of equally spaced, but that's not a cure-all. So we want to, in these next 2 chapters, we want to approach the problem, bless you, of polynomial approximation very differently than using interpolation. Okay, so for alternative approach, we're going to measure accuracy differently. Because all we're doing here is we're ensuring that the error is 0 at select points. We want to take a more holistic approach to consider what's happening in a whole interval AB, every point. So for that I need the concept of a normed linear space. Okay. Or by linear space, you can also think of it as being like a vector space. So right now I'm getting very abstract. I'm talking about not every single vector space, but vector spaces that have a notion of magnitude. Okay. So a normed vector space is a vector space V, and basically a vector space is a space that we have vectors, and the operations you can perform on them are addition and scalar multiplication. So if you have a vector space together with a norm, which is a function, and we use the double bars, and the dot here is serving as a placeholder. We enclose a vector in double bars to indicate we're taking the norm of it. And this is a norm is a function that has the vector space as its domain and the real numbers as its range. And the norm has to satisfy these properties. Because norm is meant to give the magnitude of a vector. Now, not all vector spaces are norm spaces. And for some vector spaces, you can't really define any sensible notion of magnitude. But if you can, then we call it a normed vector space. So what are the properties? A norm has to satisfy these properties to describe a magnitude. First of all, the norm of any vector V has to be non-negative. Can't have a negative magnitude. And the norm is equal to 0 if and only if the vector itself is the 0 vector. Okay. All right, so the second property is if you take a vector and scale it by some constant c, then the norm of that is just the absolute value of c times the norm of the vector. So you can, in other words, you're allowed to pull constants out as long as you take the absolute value. Okay, so c is just a real number. And finally, you have a triangle inequality. So the norm of the sum is less than or equal to the sum of the norms. Okay. So any function that you can define from a vector space to real numbers that satisfies these properties conveys an appropriate notion of magnitude. We use to describe the size of your vectors. So if a vector space has a norm, we call it a normed vector space. Okay. Now, there's two norms, there are many norms, but there are two norms in particular that we're going to focus on. One for this chapter, chapter 8, and then one for chapter 9. But I'll introduce both of them. Okay. And the concept of a norm can be used for any vector space, whatever kind of vectors you have. But we are interested in function spaces. So examples of interest to us in this chapter are, my vector space is denoted C of interval AB, and that is the space of all continuous functions on AB. So that defines a vector space. Now, the same vector space can have different norms. So one norm that I'll describe is the infinity norm. So the infinity norm of a function f, and I use the subscript infinity for it. All it is the maximum absolute value of f on AB. This is why continuity is important to assume. A continuous function on a closed interval is guaranteed to have a maximum and a minimum. So since we're assuming continuity, we can define this. Okay. Now, this is also known as the maximum norm, for obvious reasons. Those of you who plan to take 771 at some point, and let's see, well, at least 3 of you will, this is going to come up about working with function spaces and defining norms. Like Dr. Ding will work with like more abstract ones, like metric spaces and so forth, and give you annoying exercises to prove things about them, but it all starts here. Okay, so that's one useful norm. And then for the next chapter, it'll be 2 norm. So use a subscript of 2 for that. You take the integral of absolute value squared, where you optionally have some weight function that's positive on AB. And then you take a square root of all that. Okay, so this is another way to describe a norm. Now, one thing that's kind of nice is weight has to be positive and at least has to be integrable on AB. And this leads to some interesting choices. Like you could use a weight function that's actually undefined at the endpoints AB. Like the interval -1 to 1. And you use 1 over the square root of 1 minus x squared. That is singular at the endpoints. But you can still use it. And that's actually the weight function used for the Chebyshev polynomials. Okay. So when there's a weight function that's not 1, you might call this like the weighted 2 norm. And usually it should be clear from a context which weight function you're using, if any. Okay. So these are the 2 norms, and you can define other ones. Like the 1 norm would be you just integrate the absolute value. And that's of considerable interest these days in certain research areas. Okay. In 610, we get to vector and matrix norms. We'll have similar concepts to this. Okay. Now, there's some interesting properties of these norms as how they relate to each other. I'm not going to get very far, am I? Okay. Well, we'll see. First of all, we can say that the 2 norm of a function is less than or equal to the 2 norm of a function 1 times the infinity norm of that. Because what you can do is you can say that reason why is like 2 norm squared is equal to the integral of f squared, well, times the weight function. And then what I could do is I can say this is less than or equal to, and I can replace absolute value of f with its infinity norm. But that's a constant now, so I can pull it out. And what's left? The integral of just a weight function. And this is just the norm of 1 squared. Oh, this is squared also. So by taking the square root of both sides, then I get this relationship. All right. Now, one thing that's interesting is that the 2 norm and the infinity norm are not really all that equivalent. Like you might think, oh, if a function has a small 2 norm, it'll automatically have a small infinity norm, or vice versa. And for vectors, ordinary vectors in Rn, that actually is true. But for functions on the interval AB, it's not true. So one property is, for any epsilon greater than 0, no matter how small that epsilon is, and any constant, positive constant capital M, so imagine epsilon being small and capital M being really large. There exists a function f that's continuous on AB such that the 2 norm of f is less than epsilon. And the infinity norm of f is greater than capital M. So a function could have an arbitrarily small infinity norm, arbitrarily small 2 norm, and an arbitrarily large infinity norm. It's awful. And I can show you what such a function would look like. It would be a function that somewhere between AB is actually 0 most of the time and has a really tall, really thin spike. And the height of this spike is capital M. Because if you take the infinity norm of that, you look at the largest value. So you could make that spike as high as you want. But the thing is, if you make the spike really thin, then this spike makes a very small contribution to the integral, this integral that you're computing here. So if you make the height of the spike capital M, or maybe capital M plus a small amount, because I have strictly greater than here, and then I can make the width be on the order of, let's say, okay, I want the 2 norm to be epsilon, so I have, okay, so epsilon squared, like epsilon over capital M, let's see, dx, okay, so height of spike is, okay, the integrand is m squared, and then I want to get epsilon squared. Okay, so the width is on the order of epsilon over m squared. So really, really tiny, and that would actually work. So, so these kind of functions are kind of a nightmare for function approximation because it has a small norm in one case and a large norm in the other. All right, so some norms are more convenient to use than others, but this is why the infinity norm is considered more reliable. Because if a function has a small infinity norm, you know that it's small everywhere on that interval AB. Whereas a 2 norm basically can be fooled. The infinity norm can't be. But the 2 norm is nice because it's differentiable. So it's a lot more convenient to use in many applications. Because it's defined in terms of integrals and so forth. That helps a lot. So even though the infinity norm is more reliable, sometimes the 2 norm is still preferable to use.
Excuse me, I have a question.
Yeah.
So infinity norm is not differentiable.
Right, because it's depending on the value of f at a single point.
Is there any way to figure out from where we cannot differentiate? Like find the limit of it?
Let's see. For example, if you consider like the norm, whatever norm you're using, of f plus epsilon g, where epsilon is a parameter, and you take the limit as epsilon goes to 0, like something like that. You can try to define a derivative in that case, and then show that in certain cases what if it doesn't exist. Like what if you can't get, because you can perturb in any direction, and that's what makes it difficult. Because you want this to have a well-defined value no matter what g is. But g can be anything. Okay. This is easier to see, like in terms of norms of not functions but ordinary vectors in Rn. For example, if your vector space is Rn, then the norm of a vector x, called a p-norm, is you take the components, raise them to the pth power, and then you raise this, sum them up, and raise it to 1 over p power. So if p is 2, you can differentiate that with respect to each of the components of x, partial derivatives. But if p is equal to 1, you're summing absolute values. The absolute value is not differentiable at 0, because that's a corner in a graph. So that's why, and then infinity norm, there's a similar problem of there's no well-defined like tangent line or tangent space. Okay, so that's why the 2 norm is often used in applications for minimization problems. Because what are you trying to do when you minimize a function? Take a derivative and set it equal to 0. But people do try to minimize other norms too that are not differentiable, like the infinity norm, just because they have to use other approaches. But if you can minimize in that norm, you might get a better result. And I am running out of time. Well, actually, I'm at the end of the section. Wait, I want to see what kind of shape I'm in, schedule-wise. Like, how far behind am I? I'm like never calling anybody again.
It's okay. Just give me bonus.
Okay, I was supposed to get through. Okay, yeah, so I fell a little further behind. Okay, but I think I don't have many notes past this point, so we'll just see what happens. Okay, all right, but okay, now it's Siam time.
Yay!
Okay.